let us continue with the discussion from where we left. So, we are looking at the biasing problem of an active load differential amplifier, where we concluded that if you are looking at a DC bias point of an active load common source amplifier, we know that this DC point is not very well controllable, because it depends upon so many device parameters k and kp, lambda and lambda p ratios, and therefore, if you are fabricating it in a simulation, you may be getting some value, but after fabrication you will be getting completely different values, and for different versions or different copies of the same circuit, the values can be very different, and it cannot even guarantee that the transistors will be in saturation. So, we need to take help of some other biasing schemes, with the help of which I can ensure a proper DC biasing point over here. So, that technique is called common mode feedback, where we take the advantage of a differential amplifier with current mirror load, which is having a well defined DC bias point. So, let us visit our differential amplifier with current mirror load in order to be used as a common mode feedback unit. So, here we know that if you are pumping a DC bias current I bias into M5, the two transistors are going to sink IB by 2, provided you are having same DC bias condition for M1 and M2, and M1 and M2 are well matched, and therefore, both these transistors M3 and M4 are also going to have same I bias by 2, IB by 2, IB by 2 in both of them, and the IB by 2 flowing in M3 is going to establish a certain VSG for the transistor, which is basically going to be copied by M4. The same VSG apply for the M4. Therefore, this load acts like a current mirror. The M3 establishes a certain value of VSG, which is enforced by the ID by 2 provided by the bias current and provided by the symmetric biasing point enforced at the gates of M1 and M2. And now, if we also look at the other terminal of the M3 and M4, the source terminal, they are at the same potential. As a result, the VSG of M3 and M4 is at the same potential. The transistors M1 and M2 are trying to enforce the same current into them. Therefore, the ID of M3 and M4 is going to be same, VSG is same, and therefore, the VSD also must be same. That basically ensures that the VSD of M4 is exactly same or very well matched with respect to VSD of M3. Therefore, VD of 4 must be very close to VD of 3, ideally equal to the VD of 3 if these two transistors pairs are very well matched. So, differential amplifier with current mirror load is self biasing. So, it provides an output DC point which is well defined, which is equal to the VSG of M3, and therefore, we can take help of the differential amplifier with current mirror load to bias our fully differential amplifier, which is not having a well defined DC bias point. So, let us look at the overall solution that we are going to apply. So, let us draw our fully differential amplifier once again. Call this M1, M2, M3, M4, and call this M5. So, assume that the gate of M5 is anyway biased with the help of a current mirror. I am not drawing all that. And now, the first thing that we need to do is to find out or extract the common mode voltage or the common mode DC bias point for the differential amplifier output. I am assuming that the input DC points are same and both the sides are well matched. You may be having some signal applied to both M1 and M2. So, on the top of the DC bias point, you may be having some signals as well. So, you are having the VG of M1 and M2 same, the DC bias same, and on the top of that you may be having some V1 and V2, arbitrary V1 and V2 small signal, and as a result we know that the differential signal will be V1 minus V2 by 2, common mode signal V1 plus V2 by 2, and we assume that the common mode gain is poor. Therefore, we do not consider the common mode signal coming over here. Let us consider the differential signal coming over here, so call it VD, VOD plus and VOD minus. So, you will have some differential signal coming over here, and if I want to get the common mode signal. So, you are having VOD say plus the common mode level. It can also have DC plus AC. As I said, if the common mode gain is sufficient, it can also lead to some common mode signal over here. So, it may not be just a DC, it can be suppose some common mode signal VCM plus VCM. So, assume that not only DC, but you also have a common mode AC signal. So, if I want to extract the common mode signal, I can take a resistive divider, and at this point if I assume this voltage to be VO1 and this to be VO2, there is, we can write down the equation for this particular node. So, if I write this as say VT, what is the VT? So, for that I will solve the KCL in this direction. So, you just have KCL being solved over here. So, I will write VCM minus VO1 upon this R, that should be equal to the VO2 minus VCM upon R being equal, we can say that the VCM is going to be VO1 plus VO2 by 2, sorry, VO1 plus VO2 by 2. As a result, if you are having an overall common mode and differential signal, we can say that the central point over here is just going to capture the common mode signal, and that is what we want. We want to set the common mode level. Now, we have extracted the common mode signal out of this amplifier, and we want to fix it to a desired value. Now, in the subsequent discussion, I am going to assume that I am not caring for the fast varying common mode signal, because then the design becomes more challenging. So, assume that I can filter out any common mode small signal over here. So, in that case I will be remaining with only the common mode DC that I want. So, it will be the common mode DC level that I want to set. So, my target is to have a proper common mode DC level. So, if you are having a differential signal over here, its effect does not come over here, and at this point you are getting only VO1 plus VO2 by 2, which is absolutely the DC bias point or the DC common mode level at the two outputs. Now, I can apply an error amplifier over here and try to put a reference voltage V ref at the terminal, and the output of this can be made to control the gate of the PMOS. And if I ensure negative feedback in this loop, the negative feedback stabilizes the input voltage at the positive terminal close to the negative terminal or vice versa. It will make sure that these two voltages are same. So, if I ensure negative feedback, it will make sure that the two voltages over here are close together, and therefore, it will ensure that VCM is equal to Vref. And in order to make it negative feedback, I also need to make sure that the polarity of increase over here is causing the reverse action to be taken by the M4 and M3, which again tries to adjust this VCM back to the prior value. So, let us see what should be the desired polarity. So, suppose your VCM, because of some reasons, is going up as compared to the reference voltage. In that case, I would like the feedback loop to bring this VCM or the common mode voltage back to the desired value Vref. How can it happen? So, if the VCM is going up and suppose the output voltage of the amplifier also goes up, that means in that case we are going to have this as positive, this as negative. So, if the VCM goes up, the positive terminal input is going up with respect to Vref. As a result, the output voltage over here will go up. As a result, the gate voltage of these two PMOS transistors will also go up. So, what should happen to the output DC voltages over here? So, if the gate voltage of these two MOSFETs go up, remember that the DC bias point provided by M5 is fixed, the DC current flowing through M1 and M2, therefore, they are same as I bias by 2, and therefore, the DC current flowing through M3 and M4, they are also same as I bias by 2, and now you are increasing the gate voltage of M3 and M4. So, in order to maintain the same DC current I bias by 2, what should happen to the drain voltages? It should go down, because you are reducing the VSG by pulling the gate voltage up. So, VSG for both the PMOS is getting reduced. As a result, only way to maintain the same I bias by 2 current through both of them is to increase the VSD of both the MOSFETs, and therefore, it will try to pull down both the drain potentials, and as a result the common mode voltage will come down again close to Vref. So, we see that there is a negative feedback operation involved here if we make this connection to the positive terminal of the amplifier. So, we can call this as error amplifier, which is amplifying any small difference between the actual common mode signal and the desired reference signal to which we want to set the common modes, and it is controlling the gate voltage of PMOS, so that they in turn control the DC bias point at the output. So, using this configuration where a differential amplifier with differential input, but a single ended output is controlling the DC bias point at the gate of M3 and M4, which in turn are controlling the DC bias point at the two outputs, we are able to establish a well defined DC bias point Vref at the output nodes. This is the basic mechanism involved in the common mode feedback. Now, we can just replace this amplifier with our differential amplifier with current mirror load, where we can use these two input terminals of M1 and M2. The positive terminal of course is going to be the gate of M1, because if you increase the gate voltage of M1, we know that this output goes up. So, for the differential amplifier with current mirror load, this is the single ended output, and therefore, with respect to the gate of M1, we know that if you increase the gate voltage of M1, the output over here goes high. This is an non-inverting terminal, this is the inverting terminal. So, basically the midpoint VCM will be connected over here, Vref will be connected over here, and the output of this amplifier will be fed to the gate voltage of M3 and M4. So, this is the way we can realize a common mode feedback circuit, where we are establishing appropriate DC bias for the fully differential amplifier with the help of our differential amplifier with current mirror load. So, the differential amplifier with current mirror load, since it is self biased and it is having a well defined DC point, it can help the other guy having a established DC bias. Now, of course, what is the effect of this resistive voltage divider on the differential operation, that also needs to be considered. So, if I look at the differential operation, once again if I assume that okay, the DC bias point at the gate are same, well defined, differential half circuit, this point will be AC ground, and as a result if you look at the differential operation, I am going to draw the differential half circuit with the PMOS gates at AC ground. You have the NMOS gate receiving Vd by 2. Let us keep this in the view, and you are having the PMOS gate receiving Vd by 2, and this is an AC ground, and you are having the output signal over here. If you look at the condition of R, that is appearing between the output point and the VCM, which is not having any differential signal. So, with respect to the differential half circuit, this point will be AC ground, because there is no differential signal coming over here. So, in our differential half circuit, this R will come between these individual outputs and AC ground. So, in the differential half circuit, I will put this between the output and AC ground. As a result, for the differential half circuit, our gain can be modified as A differential is equal to GM 1 RO 3 parallel RO 1 parallel R, because we know that for this equivalent differential half circuit, is acting like a common source amplifier, where you have the RO of the two MOSFETs coming into picture between the drain and the AC ground. So, you have RO 1 over here, likewise you have RO 3 over here. VDD is effectively an AC ground for the small signal analysis. So, RO 3 over here. So, basically RO 1, RO 3 and R all appear between the output point and the respective AC grounds, and therefore, the overall gain is just GM 1 times RO 3 parallel R, and therefore, definitely if we want to maintain large open loop gain, we must make sure that R is sufficiently larger as compared to RO 3 and RO 1, and now this requirement will just definitely make us think that of course, now there are going to be a lot of constraints, because we are looking for lower current, so that we can reduce our power dissipation. We also want larger open loop gain, that would also enforce lower bias current, and that would mean very large RO 1 and RO 3. So, in 180 nanometer technology, if you are going for bias currents of the order of 10 microampere, RO values can easily approach hundreds of kilo ohm to 1 mega ohm, especially when you use longer channel lengths. So, we will see that noise constraint also enforces longer channel lengths, and that would make the RO1, RO3 pretty large, and that would mean that if you really want to use the resistive divider to extract the common mode voltage, the R value required over here will also be very large, and then the expected value can range from mega ohm anywhere between mega ohm to tens of mega ohms, which will once again will not be very practical from the point of view of integrated circuit design. Therefore, we can look for alternate techniques where we can avoid use of such resistive dividers and rather go for active components only in the feedback loop. So, let us look at alternate scheme where we can avoid the use of such large passive resistors in order to determine the common mode feedback. So, let us just have a brief overview of what we are going to do. So, we are going to basically have our error amplifier itself being capable of extracting the common mode signal. So, here we are relying on this R values to extract the common mode signal, and then it is fed to a simpler error amplifier. Now, if we can translate or we can outsource this common mode extraction to our error amplifier, then the job becomes simplified. We may not rely on R. That is the strategy we are going to use. We are going to incorporate this common mode extraction inside our error amplifier, so that we do not have to rely on these large resistors in order to achieve common mode feedback. So, let us look at that in our next module.